Everybody, Edward Scheinerman's textbook was looking for a direct proof to this that's fairly obvious if you just examine a new, he was looking for a direct proof. Let me get that written down if I can possibly do that any faster. Proof. He was looking for a direct proof, and basically this just relies on, do you know the definition of what it means for something to be composite? And I should also stipulate that k, of course, is a natural number. N is a natural number, k is a natural number. We're supposed to show that a number squared minus 1 is composite. Now, there is a slight problem. Notice that if we take k equals 2 right here, and 2 kind of mucks up things quite a bit for a lot of number theory proofs. But notice if k is equal to 2, we actually get a prime number. And this difference of two squares formula predicts the factorization, as it should. 3 times 1, right? So you see, obviously 3 is a prime, and so we have to exclude k equals 2. All right, so, but notice that when we get to k equals 3, it reaches something that's quite believable. K is equal to 3. 3 squared is 9, so this would be 8. Is equal to 4 times 2, and that's literally the definition of composites. Okay, if there's two proper divisors, or at least one actually is technically, that's equal to 4 times 2. 2 and 4 both being less than 8. Notice that a prime number doesn't have that going on. That's the distinction between a composite, okay? But anyway, we're supposed to prove this in general. It's very easy to believe that this is true based on just this difference of two squares factorization. And also, k plus 1 and k minus 1 are proper divisors in the event that k is greater than 2. So we've actually proved it, okay, QED. It's a direct proof, follows immediately from the definition of what it means to be composite. Now, just a little side note, the A and B's don't necessarily have to be distinct in the more general case, not the squared minus 1 case. For example, if you have 49, you know that that's definitely composite, right? Because it has a divisor of 9, but it has just a divisor of 9. So you see, 7 times 7 would be your A times B. So in general, you can't assume A and B is distinct values. You can only assume there's at least a single divisor strictly between 1 and the number that is composite. Anyway, we're done with the proof. The direct proof. Hope you enjoyed.